Kannan Gopalakrishnan. He was working as a senior architect at Engineering Design Research Centre, L&T Construction, India's largest construction company. He's also worked on projects ranging from institutional buildings to international airports, apartment complexes to aircraft hangars. He's also attended 3 international conferences and 2 national conferences, and has also presented technical papers at the Jawaharlal Nehru University, Delhi, and the MSRIT, Bangalore. He's also won the national championship at Archaman at the India's largest architecture quiz. Sir Kannan Gopalakrishnan currently runs a design firm, Habitat Design Studio, and he is also a visiting faculty at the renowned architecture schools in Tamil Nadu.
Welcome back to UGC lecture series. This is AR 6006 Structure and Architecture, and we are still in unit 2, which covers history of structural design in the post-industrial period. We are on lecture number 8, and in the previous episode, if you could remember, we saw the works of early structural masters of Pier Luigi Nervi and Robert Mailliat. These 2 masters were working with bridges, steel and naked structures, and they were the masters, early masters and the pioneers of structural design and architecture. Following their lead, there were more than a dozen architects who were working on famous projects and who revolutionized the design, structural design and architecture in the years to come. We will be looking at a few people in this section, and right now in this episode we are looking at 2 people, Felix Candela and Eero Saarinen. So, straight away we would just jump into and look at the works in early life and other contributions made by Felix Candela. Felix Candela was a Spanish Mexican architect. He studied from the Madrid School of Architecture in Spain, where he was born. He was famous for the development of Mexican architecture and structural engineering. He was also famous for development of thin shells made of reinforced concrete known as cascarons. Let's have a quick look at his early life and career. Felix Candela was born in Madrid, Spain in the year 1910. He graduated in 1935 from Madrid Superior Technical School of Architecture. He then travelled to Germany to study architecture further. There he developed a very keen interest in geometry, and he always had a very keen sense of mathematical precision in his drawings. He also started teaching other fellow students in his private lessons during his study in Germany. Later he moved to Mexico after the Spanish Civil War. Looking at what he is famous for, he is famous for thin shell structures made of reinforced concrete called cascarons. So, cascarons are basically reinforced concrete structures which are extremely efficient in a dome or a shell like structure. Let us look at the efficiency of these structures and let us look at why they are very efficient here, because the shape pretty much eliminates all the tensile forces in the concrete, because we know that from our earlier episodes and we know from our earlier studies that concrete itself is very bad in tension. That is why we require an element called steel, which is to be reinforced with concrete, so that the reinforced cement concrete itself as a compound structure becomes capable of handling both compression and tensile structures. Here the concrete structure, this type of a thin cascaron structure, eliminate the tensile forces completely in concrete, thereby making concrete more efficient in taking loads. So, it is like a arch shaped structure. We saw in our earlier lecture video that in an arch the tension element is completely lost. All the forces are completely compression forces, where the load transfer is from one element from the top to the next element on the bottom, and then it just transfers all the way to the base, whereas none of the elements actually carry any tensile force. Similar thing is what is happening in these cascarons. So, around 1950, Candela's company went to design laminar structures. Candela did most of his work in Mexico throughout the 1950s and into the early and late 60s. He was responsible for more than 300 projects and he was responsible for more than 300 works and over 900 projects in this time period. Let's look at one of his famous works. His first and famous work is called the Pavilion of Cosmic Rays. It's located to the south of the National Autonomous University of Mexico. Currently, it's in the same good condition in which it was proposed. The pavilion is a very thin reinforced concrete double curvature structure. It has two curvature. The first curvature here is the one which you see here. This is the first curvature, and the second curvature is what you see over here. This is curvature number 2. So, this structure is curved both on this axis, at the same time it is curved in this axis. So, due to the very thin reinforcement concrete and its double curvature and it is based on a structural principle or a mathematical component called the hyperbolic paraboloid. That is the concept which the structure is based on. The Pavilion of Cosmic Rays is proposed using a double layered curved roof warped structure instead of a cylindrical structure which was originally projected by architect George Gonzalez Reina. The initial projection of this project was a cylindrical structure in which like a vault like structure, a catenary vault like structure, where the structure itself will have half of a cylinder and this half a cylinder will have a single curvature. That was what was proposed by architect George Gonzalez. But later Candela came and changed the form to a hyperbolic paraboloid. He justifies the construction of a hyperbolic paraboloid in the geometric ray since it would provide the stiffness, strength and the necessary stability that the structure needed. So, he is talking about three major components here. He is talking about stiffness, strength and stability. They are three different things. Often stiffness, strength and stability is confused with one another, but then Candela clearly differentiates these three things and he thinks that only the use of the double curvature, the one curvature over here and another curvature over here, only by the use of these two curvature in the single building, he is able to achieve all the three components which he mentions: stiffness, strength and the stability. The shell has 12 meters, the shell is 12 meters long and 10.75 meters wide. The cover of this laboratory, specializing in the measurement of neutrons, should respect the condition of not to exceed 15 millimeters thick at its highest point to fulfill its role optimally. Access is via a reinforced concrete staircase leading to the first bay of the building, where there is a lobby that connects to an external cubicle and two laboratories. These are some of the pictures of the Pavilion of Cosmic Rays, the structure, and we can see the staircase at the rear end of this picture. There is a close-up view over here. The staircase made of reinforcement concrete which leads to the laboratory on the top, and this is the setting of the university, and we can see the frame of reference where our little pavilion is placed over here. The pavilion consists of a foundation based on an isolated footing which leads to two bays from the three grid frames which reinforce concrete columns that clearly divides the space into two. There are three frames, 1, 2 and 3, three frames which clearly divides the space into two. The one space is over here and another space is over here. So, clearly there are two bays which are formed from the three rigid frames of reinforced concrete. The laminar structures or reinforced concrete shells derive their stiffness and strength with respect to the geometry they acquire by allowing tangential stresses that makes the bending so small that it is considered negligible. There is practically no bending that is happening on the structures because of the tangential stresses which the whole structure allows for. So, that is why the bending stresses are considered negligible in the structure, and that is what makes the structure very stable. Let us move on to the next project. It is called L'Oceanographique. It is an oceanarium situated in the east of the city of Valencia, Spain, where different marine habitat are represented. The Oceanographique is the largest such structure in Europe, with a surface of 1,10,000 square meters and a capacity of 42 million liters. This is the building. This is how the building looks. Look at the use of thin shells called cascarons, and look at the way he has arranged all these cascarons in a spiral fashion, and the striking use of glass with respect to the water, the blue color, the reflective blue color of the glass with respect to the reinforced concrete, naked color of the concrete is clearly amazing. These are some of the pictures of the interior of the structure, where he tries to use different kinds of support systems for the roof. Look at how complex systems of structure he has arrived for the interiors. And this is the basic shell structure without the glass roof, and this is how the building looks like if there is no glass enclosure provided for the building. And on the bottom picture you see the glass enclosure provided with the setting and everything, but on the top picture we can clearly see how the actual structure behaves. We can see the point where the structure meets the ground. There are only few points where the structure meets the ground, but still the whole structure, the whole concept is able to maintain the entire structure, entire area by very minimal number of contact points, and this is the structural drawing of the building. These are some of the other buildings which are designed by Felix Candela. So, now let us move on to the next architect whom we are seeing today. We will be looking at the projects and life and works of architect Eero Saarinen. Eero Saarinen was a Finnish American architect. He studied at the Cranbrook Academy of Art. He was the son of an influential Finnish architect Eliel Saarinen and his second wife Louise. He became friends with fellow students such as Charles and Ray Eames, also with Florence Knoll, whom he later collaborates with to create furniture and get it manufactured. Can we look at the early life and career of Eero Saarinen? He grew up in Michigan, where his father was a teacher at the Cranbrook Academy of Art. He took courses in sculpture and furniture design there, and he also went on to study sculpture at the Académie de la Grande Chambre in Paris. He then went on to study at the Yale University, Yale School of Architecture. He completed his studies in the year 1934, and he became a naturalized citizen of the United States subsequently in 1940. Saarinen first started his design career in the field of furniture design. He received his first critical recognition in the field of furniture design for a chair that he designed together with Charles Eames in 1940. They received the first prize for the chair. The one on the left here, this chair is called the womb chair, and this chair is called the tulip chair, and this is from a series called the pedestal series. The first major building which our architect Eero Saarinen designed was the Crow Island School. The school has 4 wings emerging from a central building with common rooms. This design allows each classroom to have its own courtyard, and each wing will have its own playground. The aesthetics and the form became a template for mid-century schools, although the planning or educational system itself did not catch on, but the aesthetics and form definitely did catch on, and it became a template for mid-century schools later on. If you look at the building here, note the way he uses brick as one of the very strong elements here. The way he uses brick and the way he positions windows horizontally, and the planning itself, like we saw here, it has 4 wings emerging from a central building. which means that you can have courtyards for each of the classroom and a playground for each of the 4 wings. The next famous building that we are going to look at in Eero Saarinen's career is the GM Technical Center. GM is General Motors. The original idea of an office block was abandoned during the planning phase. Any office block that was designed at that particular point of time followed an architecture that was called modern architecture, and this modern architecture had very strict rules on how a building must look and how a building must feel like, the concrete, the glass, and the way it is created. The idea of an office block was completely abandoned. The eye-catching accent was now placed by a large fountain and a silvery water tower placed in an artificial lake which is created here. This is the artificial lake, and there is a large fountain and a water tower which is placed here. And the picture on the right here shows the interior reception where the custom made furniture for the receptionist table, and we can see a staircase in the background. The building was furnished with furniture pieces designed by Eero Saarinen himself, and this is another winding spiral staircase which you see in the interiors of the General Motors Technical Center. Situated on a square mile of a countryside, this extraordinary assemblage of 20 buildings and a sizable man-made lake, complete with fountains and a handsomely modelled stainless steel sheathed water tower, has been called a coordinated research town in itself, and it is also called an industrial Versailles. Particularly noteworthy is the use of walls and panels of vivid colors as enlivening accents inside and out. The next famous building that we are going to look at in the architectural career of Eero Saarinen is the David S. Ingalls skating rink inside the Yale University campus. This skating rink is characterized by a sweeping dome roof, was designed by Eero Saarinen. He himself was a graduate of the Yale school, and this building is lovingly known as the Yale Whale, probably because of the shape of the building, shape of the roof of the building, and the color and the striking contrast this gives with the sky behind. Though the rink is seemingly heavy and brutal, it is truly a tensile structure. The main structure comes from a 290-foot long central arch which acts as a backbone of reinforced concrete. The central arch is this one, which acts like the backbone, and from there we have subsequent structural systems that carry the entire load of the structure. You see the central arch over here and the subsequent structural elements on this picture. The next famous building that we are going to look at is the MIT Chapel. MIT Chapel is situated inside the Massachusetts Institute of Technology in Cambridge. It is a non-denominational chapel designed inside the campus. Even though it is a very small building, it is noted as a successful example of mid-century modern architecture. The sheer manipulation of light and its focus on the blazingly white marble altar over here, this created a place of mystic quiet. The exterior of a building is very simple, with brick as a material, with a cylinder which is supported by small arches at the base of the building, small arches which you see over here, and it is surrounded by a small thin concrete moat, and it is surmounted by an aluminum spire on the top here. It is completely windowless. It has only one opening right in the middle which provides light directly onto this altar, blazingly white marble place. That is all that creates the magic. From the outside, the chapel is a simple windowless brick cylinder set inside a very shallow concrete moat. It is 50 feet in diameter and 30 feet high, topped by an aluminum spire. Saarinen chose bricks that were rough and imperfect to create the texture effect. Look at the texture that is created on the wall here when there is light being focused. This texture is created specifically by Saarinen to get the textured effect. The next important building that he designed is, of course, the St. Louis Gateway Arch. The Gateway Arch is a 630-foot monument in St. Louis. It is clad in stainless steel and built in the form of a catenary arch. It has many accolades to carry for itself. It is the world's tallest arch, the tallest man-made monument in the Western Hemisphere. It is Missouri's tallest accessible building. It is the centerpiece of the Jefferson National Expansion Memorial. A soaring curve in the sky that links the rich heritage of yesterday with the richer future of tomorrow brings a new purpose and a new sense of urgency to wipe out every slum. That is what the building is described as. Here you can look at the picture in the twilight, in the night sky, the reflection of the Gateway Arch in the water, and here we can look at the Gateway Arch as a background of Jefferson National Memorial. The architecture study about Eero Saarinen is never complete without the study of the TWA terminal. TWA terminal is also called the Trans World Airlines Flight Center. Although it was opened in 1962, it was abandoned later. The portions of original complex have been demolished, but the Saarinen designed head house has been renovated and it is partly encircled by a replacement terminal building. The building that you see here is shaped like a bird taking a flight. The bird with a beak, with its two legs and claws, with its wing on either sides, ready to take a flight. How interesting is this form, especially when you want to design an airport terminal building. You take the inspiration from a bird just about to take a flight, and then you design a beautiful building with that as your inspiration. How great is that? This is the building from a top angle. Now you can clearly see the head of the bird and the beak, the two wings of the bird and the tail of the bird. You can see one of its legs over here, the other leg is hidden by the body, and this is how beautiful the structure looks. It is so beautiful that both the interior and the exterior were declared as New York City landmark in 1994. It is called the Grand Central of the jet age, and it is also called the monument to human throughput. The prominent wing-shaped thin shell roof over the head house or the main terminal is the one that catches the eye of any observer. The unusual tube-shaped departure-arrival corridors were originally wrapped in red carpet. Tall windows enabling expansive views were provided to view the departing and arriving jets. The thin concrete shell, which inspired Saarinen to develop curved edge ceramic tiles conforming to the curvilinear shape, was specifically designed for this building. This building straddles many styles of architecture in the future, such as futurism, googie architecture, fantastic architecture. This particular architecture style which Eero Saarinen followed is also called neo-structural expressionism. So let us look at some of the pictures of TWA terminal. These are the interiors of the building, and this is another exterior where it is well lit, and you can still see the logo of the TWA on the right hand side over here. The furniture were again designed by Eero Saarinen himself. Look at the bold use of colors red and white on the interiors, and this was the narrow passage that he was talking about earlier, which was red carpeted completely. If you look at the interior of this building, look at the sweeping curves and the straight lines on the picture here. This is the kind of architecture that creates a sense of greatness in every person. The moment you enter the airport terminal, you see all these sweeping curves and elegantly designed staircases, handrails, these furniture. That is when you get inspired to life itself. From this lecture, we understand the complex structural marvels which were designed by famous masters such as Saarinen and Candela. We saw the legendary architects' works, we saw their life, we saw some of the famous buildings that they designed. With this understanding, we should be able to answer some of the questions that are there on the slide here. How do we know Candela in the field of architecture? Explained with sketches of his most famous works. How do we know Eero Saarinen in the field of complex structural architecture? Explained with sketches of his most famous works. What is neo-futuristic expressionism? What are cascarons? Explained with sketches. With this, we come to an end of lecture 8 of the series, and I look forward to meeting you in lecture 9 with another master, famous designer, and a lot of other complex structural principles. So, thank you.